In Chapter 3, we're going to look at prior information and subjective probability. So, we want to quantify our knowledge about this unknown parameter, and we've talked about how we can do that by trying to put together a distribution on the parameter space, which we call pi, or pi star, we've called it. And since theta actually is a constant, then it's not really a true distribution because the theta is not actually random. So we have to kind of talk about how we're looking at things here. So how would we interpret something like this probability? So theta here is the unemployment rate for next year, right? Whatever that number is, it's just going to be constant. So what does it mean to say that the probability that theta lies between 2% and 4% is, whatever? Well, the theory of subjective probability enables us to do this. And it can be used when the frequency perspective of probability does not actually apply. So with subjective probability, we use our prior knowledge and we make an educated guess at the distribution pi of theta. So let's suppose we have an event E. So E is some event or some subset of the parameter space, which we think of as an event, and we want to determine the probability of this event. One way that we can do this is to think about the quotient of the probability of the event E to the probability of the event E complement. And then we have to ask ourselves, how much more likely do we feel this event E is as compared to E complement? And so let's say we feel that the probability of E is 4 times as likely as E complement. So this event E is 4 times as likely to occur as not to occur. Then that would lead us essentially to a system of equations, 2 equations and 2 unknowns, right? Because we would have the probability of E equals to 4 times the probability of E complement. And then as always, the sum of those two must be 1. And so you solve that system of equations, and then now you have probabilities assigned to each one. Another method which can be used to help determine subjective probability is to go back to the idea of utility and the idea of betting. And so you suppose that there's some value z in the interval from 0 to 1, and that will be lost if the event E occurs, and then 1 minus z will be 1 if the event E does not occur. So, and then you just try to determine an appropriate z value. They describe this in the textbook, and you can read about it at the bottom of page 75. And so we wish to choose z so that we consider this to be a fair gamble. And then in that case, based on your utility function, you just work it out to where the expected utility would be 0, because if you feel that that gamble is fair, then your expected utility should be 0. And then from there, you can determine the probability of E. And these methods are useful at times to determine these subjective probabilities, but we are going to focus on methods to determine a prior density for theta. And then also, how do we combine that with the data to update our understanding of theta and the distribution thereof. Now, these techniques are useful for determining the prior distribution if our parameter space is discrete. So in what follows, we're going to focus on the case where the parameter space is continuous. The histogram approach is one where we could deal with the continuous case. So let's suppose that the parameter space is an interval of the real numbers, and we're going to divide it into subintervals. And then for each subinterval, we could use our prior knowledge and then subjectively determine the probability of each interval. And so, in a sense, we're manufacturing a pseudo-discrete problem. Now that makes sense. And then we can use the histogram to sketch a smooth density that conforms nicely to the histogram.